Yes, good morning, dear students. Welcome for the physics class. So, in the previous class, we have discussed about the reason for ferromagnetism, paramagnetism, and diamagnetism. Right? A ferromagnetic material means these are the materials which are strongly attracted by the magnets. The reason for that behavior is the domain theory of ferromagnetic material. So domain means it is a group of atoms. Atoms will call there as a dipoles. The group of dipoles which have been aligned in a same direction is called as a domain. So in a ferromagnetic material, it is made up of domains. Means a group of atoms which are aligned in a same direction in one domain. So number of such domains together we are going to get the ferromagnetic material. In the absence of external magnetic field, all the domains have been arranged in different directions. Right? Their net magnetic moment is going to cancel with each other. But when we apply the external magnetic field, that will force all the domains to arrange them in a particular direction, that is in the direction of magnetic field. Then that material will becomes the giant domain. So now that will be strongly attracted by the magnets. And next comes paramagnetic material. So these are the materials which are weakly attracted by the magnet because there will take the theory of dipoles to explain the cause for that paramagnetic behavior. So there all the dipoles means all the atoms, will call them as a dipoles, which are present inside the paramagnetic materials. They will arrange partially in the direction of external magnetic field. That partial alignment is the reason for their weak attraction by the magnets. And next one is the diamagnetic material. There inside the diamagnetic material, the magnetic field will be induced in the opposite direction to that of the external magnetic field. So that opposite field which has been induced in a diamagnetic material is the responsible for the weak or the feasible repulsion between the magnet and the diamagnetic material. Okay, now in this class we'll study the properties of paramagnetic, ferromagnetic and the diamagnetic materials, and also some of the law regarding these magnetic materials. So we'll come across the first law, that is Curie's law. Curie law. Curie law. So here Curie law is tells about the paramagnetic materials. Okay, so here the Curie law is regarding the paramagnetic materials. Okay, so what it tells, Curie's law states that the susceptibility of the paramagnetic material. What do you mean by susceptibility? So we can define it in a way that it is the ratio of magnetization to the magnetic intensity. In general, we can say that it is the ability of the material to become a magnet. How easily a material can be magnetized, that is called as the susceptibility. Okay, so then here the Curie's law is telling about the ability of the material. Which material? Paramagnetic material being magnetized material. Okay, being magnetized or being or inducing the magnetic property. How easily it will induce the magnetic property, right? So here Curie's law states that the susceptibility of a paramagnetic material is inversely proportional to the absolute temperature. What do you mean by absolute temperature? Absolute temperature means it is the temperature in which the material will be in its lowest possible energy state. The material will be in its lowest possible energy state. That temperature, that corresponding temperature is called as the absolute temperature. Okay, so here the susceptibility, look here, we can indicate with the letter psi. So that is inversely proportional to the absolute temperature, that is T. So what do you mean by this statement? So as temperature increases, the susceptibility decreases. What it indicates? As we increase the temperature of the paramagnetic material, its ability to be magnetized becomes low, or its ability to become magnetized will decreases. Why? What is the reason? So look here, we already studied the structure of paramagnetic material. So in this, initially the dipoles will be in a random manner, aligning in the random manner. So that's why the net magnetic moment of the material will be zero. But when we apply the external magnetic field, it will force those dipoles to align themselves partially along the direction of external magnetic field. Okay. Now, here the dipole don't have much energy to overcome the external magnetic field. So that's why what happens when we apply the external magnetic field, those dipoles were going to align themselves partially, that is partially align themselves along the direction of magnetic field. But when we increase the temperature above the absolute temperature, what happens? Those dipoles which have been already aligned partially, or which are trying to align themselves partially, will get the much of energy. Then what happens? They won't listen the words of external magnetic field. They won't agree with the external magnetic field because the external magnetic field is weak. Then what happens? Again they turn themselves in a random manner. No, if you want to turn them partially along the direction of field, what we have to do? We need to increase the magnetic field, external magnetic field. What it indicates? The susceptibility is decreasing, means the ability of being magnetized is decreasing. Is it clear? Right? ನೋಡ್ರಿ, ಈಗ ಟೆಂಪರೇಚರ್ ಕೊಟ್ಟೆ ಅಂತಂದ್ರೆ ಡೈಪೋಲ್ಸ್ ಏನಕ್ಕೈತಿ, ಎನರ್ಜಿ ಸಿಗ್ತೈತಿ. ಎನರ್ಜಿ ಸಿಕ್ತು ಅಂತಂದ್ರೆ ಅವು ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡಿನ ಮಾತು ಕೇಳಂಗಿಲ್ಲ, ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡಿಂದ ಡೈರೆಕ್ಷನ್ನಾಗ ಅಲೈನ್ ಆಗಂಗಿಲ್ಲ. ಏನು ಪಾರ್ಷಿಯಲಿ ಅಲೈನ್ಮೆಂಟ್ ಇತ್ತಲ್ಲ, ಸೊ ಈ ಥರ ಪಾರ್ಷಿಯಲ್ ಅಲೈನ್ಮೆಂಟ್, ಇಫ್ ಇಟ್ ಈಸ್ ದ ಡೈರೆಕ್ಷನ್ ಆಫ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್, ಇಟ್ ಈಸ್ ದ ಡೈರೆಕ್ಷನ್ ಆಫ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್, ರೈಟ್? ದೆನ್ ಈ ಅಲೈನ್ಮೆಂಟ್ ಏನು ಪಾರ್ಷಿಯಲ್ ಅಲೈನ್ಮೆಂಟ್ ಇತ್ತಲ್ಲ, ಏನಾಗುತ್ತೆ, ನಾವು ಟೆಂಪರೇಚರ್ ಇನ್ಕ್ರೀಸ್ ಮಾಡಿದ್ವಿ ಅಂತಂದ್ರೆ ಈ ಡೈಪೋಲ್ಸ್ ಏನ್ ಮಾಡ್ತಾವು, ಆ ಟೆಂಪರೇಚರ್ ನಿಂದ ಎನರ್ಜಿ ತಗೋತಾವು. ದಿಲ್ ಗೆಟ್ ದ ಎಕ್ಸ್ಟ್ರಾ ಎನರ್ಜಿ. ಅವಾಗ ಏನಾಗತ್ತೆ, ಅವು ತಮ್ಮನ್ನ ಎತ್ತಬೇಕಂತ ಹೊಳಸ್ಕೊಳಕ್ ಸ್ಟಾರ್ಟ್ ಮಾಡ್ತಾವ. ಹೊಳಸ್ಕೊಳಕ ಸ್ಟಾರ್ಟ್ ಮಾಡ್ತಾವು, ಲೈಕ್ ದಿಸ್. ಈ ತರ ಆಗ್ಬಿಡ್ತೈತವ. ನಾವೀಗ ಅವ್ನು ಮತ್ತೆ ನೆಟ್ಟಗ ಮಾಡ್ಬೇಕು ಮೊದ್ಲಿನ ತರ ಅಂದ್ರೆ ಏನ್ ಮಾಡ್ಬೇಕು, ಎಕ್ಸ್ಟ್ರಾ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಅನ್ನ ಕೊಟ್ಕೊಂತ ಹೋಗ್ಬೇಕಾಕೈತಿ. ಹೌದಾ? ಎಕ್ಸ್ಟ್ರಾ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಕೊಡಾಕತ್ತೀವಿ ಅಂದ್ರೆ ಅದರ ಅರ್ಥ ಏನು, ಸಸೆಪ್ಟಿಬಿಲಿಟಿ ಡಿಕ್ರೀಸ್ ಆಗೈತಿ ಅಂದಂಗೆ. ರೈಟ್? ಆಸ್ ಟೆಂಪರೇಚರ್ ಇನ್ಕ್ರೀಸಸ್, susceptibility decreases, means easiness of being a magnet or being a magnetized, easiness of being a magnetized will decreases. Okay, it will become more complicated. So that will be told by Curie law. So now, in order to remove this proportionality sign, we'll insert a proportionality constant, that is C. Okay. So what do you mean by C here? C means it is the Curie constant. C means it is the Curie constant. It is material dependent factor. It is not same for all the material. This Curie constant is not same for all the materials. It is different for different materials. As you know, gravitational constant, it is the constant for all the materials, right? Universal constant. Planck's constant, that is universal constant, that is same for all things. But here, for Curie constant, that is not like that. It is a material dependent factor, materialistic factor. It varies from material to material. Okay, so C is Curie constant. Is it clear? So this is about the Curie law, and next we'll move towards the Curie temperature. Okay, the next concept is Curie temperature. Curie temperature, or else we can also call it as a Curie point or a critical temperature. Both are same, one another same. Curie temperature ಅಂದ್ರೆ ಒಂದೇ, Curie point ಅಂದ್ರೆ critical temperature ಅಂದ್ರೆ ಒಂದೇ. ಸೊ ಯಾವುದ್ರ ಬಗ್ಗೆ ಹೇಳ್ತದೆ ಇದು? ಯಾವ ಫ್ಯಾಕ್ಟರ್ ಬಗ್ಗೆ ಈ Curie temperature ಮಾತಾಡ್ತದೆ? ಏನು Curie temperature ಅಂತಂದ್ರೆ ಇಟ್ಸ್ ರಿಗಾರ್ಡಿಂಗ್ ದ ಟೆಂಪರೇಚರ್. ಓಕೆ, ಇಂಪಾರ್ಟೆಂಟ್ ಒನ್. ದೇ ಮೇ ಆಸ್ಕ್ ಫಾರ್ 1 marks. ಡೆಫಿನಿಷನ್ ಕೇಳ್ತಾನ, ವಾಟ್ ಈಸ್ ಕ್ರಿಟಿಕಲ್ ಟೆಂಪರೇಚರ್ or what is Curie temperature, what is Curie point ಅಂತ ಹೇಳಿ ಕೇಳೋ ಚಾನ್ಸಸ್ ಇರ್ತವೆ ಫಸ್ಟ್ 1 marksಗೆ. ಸೊ Curie temperature ಅಂತ ಹೇಳಿದ್ರೆ ಇಟ್ ಈಸ್ ದ ಟೆಂಪರೇಚರ್ above which the ferromagnetic material behaves like a paramagnetic material. Listen carefully. Okay, so Curie temperature means it is the temperature above which the ferromagnetic material behaves like a paramagnetic material. Paramagnetic material. Is it clear? Why it is so? Look here, we have already studied that the reason for ferromagnetism. There we are studied about the domain structure. Domain structure means it's a group of atoms having the same directional alignment. Okay, so when the temperature exceeds the Curie temperature, means when we increase the temperature above the Curie temperature, above some particular temperature, let's neglect about the Curie temperature or Curie point or whatever it may be. So just consider a temperature which is increasing up to certain limit. The ferromagnetic material remains with its original properties, but above certain limit, what happens? They'll start behaving like a paramagnetic material. Why? Because above that limit, if we increase the temperature, the dipoles which are in the domain, means the dipoles having the same direction within the domain will get the extra energy by means of increasing temperature. Then what happens? They'll start aligning in a random direction. Then what happens? The domain structure decays. If the domain structure decays, means what happens? The dipoles will be seen like or dipoles in the ferromagnetic material or domains in the ferromagnetic material will be seen like dipoles in the paramagnetic material. Right? ನೋಡ್ರಿ, ಈಗ ಡೈಪೋಲ್ಸ್ ಸೇಮ್ ಡೈರೆಕ್ಷನ್ ಆಗಿದ್ರೆ ಅದಕ್ಕೆ ಡೊಮೈನ್ ಅಂತೇಳಿ ಕರಿತೀವಿ ನಾವು. ಸೊ ನಂಬರ್ ಆಫ್ ಡೊಮೈನ್ಸ್ ಕೂಡಿ ಒಂದು ಫೆರೋಮ್ಯಾಗ್ನೆಟಿಕ್ ಮಟೀರಿಯಲ್ ಆಗಿರ್ತದೆ. ಡೊಮೈನ್ಸ್ ಒಳಗಡೆ ಎಲ್ಲ ಡೈಪೋಲ್ಸು ಸೇಮ್ ಡೈರೆಕ್ಷನ್ನಿಗೆ ಇರ್ತಾವೆ. ರೈಟ್? ಈಗ ನಾನು ಎಕ್ಸ್ಟ್ರಾ ಎನರ್ಜಿ ಕೊಟ್ಬಿಟ್ಟೆ ಅಂದ್ರೆ ಏನಾಕೈತಿ, ಒಂದು ಡೊಮೈನ್ಯಾಗ ಒಂದು 4 ಡೈಪೋಲ್ಸ್ ಅದಾವಂತ ಇಟ್ಕೊಳ್ರಿ, 4 ಫ್ರಮ್ ಲೆಫ್ಟ್ ಟು ರೈಟ್ ಡೈರೆಕ್ಷನ್ಯಾಗ ಅದಾವಂತ ಇಟ್ಕೊಳ್ರಿ. ಒಂದು ಡೊಮೈನ್ಯಾಗ 4 ಡೈಪೋಲ್ಸು. ಈಗ ನಾನು ಎಕ್ಸ್ಟ್ರಾ ಟೆಂಪ್ರೇಚರ್ ಕೊಟ್ಟೆ ಅಂತಂದ್ರೆ ಎನರ್ಜಿ ಗೇನ್ ಮಾಡ್ಕೊತಾವ. ಗೇನ್ ಮಾಡ್ಕೊಂಡು ಏನಾಗ್ತದೆ, ಅವೇನು ಲೆಫ್ಟ್ ಟು ರೈಟ್ ಡೈರೆಕ್ಷನ್ ಇತ್ತಲ್ಲ, ಒಂದು ಏನು ಮಾಡ್ತೈತಿ, ಅಪ್ವರ್ಡ್ ಡೈರೆಕ್ಷನ್ಯಾಗ ನಿಂದಿರ್ತೈತಿ, ಇನ್ನೊಂದು ಡೌನ್ವರ್ಡ್ ಡೈರೆಕ್ಷನ್, ಮತ್ತೊಂದು ರೈಟ್ ಸೈಡ್ ಡೈರೆಕ್ಷನ್. ಅವಾಗ ಅದಕ್ಕೆ ಡೊಮೇನ್ ಅನ್ನಕ್ಕೆ ಬರ್ತದ? ಇಲ್ಲ. ಯಾಕೆ ಹೇಳ್ರಿ? ಎಲ್ಲ ಡೈಪೋಲ್ಸು ಸೇಮ್ ಡೈರೆಕ್ಷನ್ನಾಗಿಲ್ಲ. ಹೌದಾ? ಸೊ ಅವಾಗ ಏನಾಕೈತಿ, ಡೊಮೇನ್ ಸ್ಟ್ರಕ್ಚರ್ ಹಾಳಾಗಿ ಹೋಗ್ಬಿಡ್ತೈತಿ. ಇಟ್ ವಿಲ್ ಡಿಕೇಸ್. ಈ ಡೊಮೇನೇ ಇಲ್ಲ ಅಂತಂದ್ರೆ ಯಾವ ಕೇಸ್ ಬಂತದು? ಪ್ಯಾರಾಮ್ಯಾಗ್ನೆಟಿಕ್ ಮಟೀರಿಯಲ್ಸ್. ಯಾಕಂದ್ರೆ ಪ್ಯಾರಾಮ್ಯಾಗ್ನೆಟಿಕ್ ಮಟೀರಿಯಲ್ಸ್ನಾಗ ಡೊಮೈನ್ ಸ್ಟ್ರಕ್ಚರ್ ಇಲ್ಲ. ಹೌದಾ? ರೈಟ್? ಸೊ ದಟ್ ಈಸ್ ದ ರೀಸನ್. ರೈಟ್? ಸೊ ferromagnetic material will behaves like a paramagnetic material because the temperature is high. The temperature is high. It has been exceeded a limit. So that limit is called as the Curie temperature or the Curie point, the critical temperature. Is it clear? So next we will discuss about the Curie-Weiss law. Curie-Weiss law. Curie-Weiss law. Curie-Weiss law. So whenever the temperature is below the Curie temperature, at that time ferromagnetic material will remains ferromagnetic material only. It will remains with the ferromagnetic property only. But above the Curie temperature, the susceptibility of the ferromagnetic material will be explained by Curie-Weiss law. So here Weiss means it is also the name of the scientist. Okay? So whatever domain theory we have studied in a ferromagnetic material, we can also call it as Weiss domain theory. Right? So here the susceptibility of a ferromagnetic material above the Curie temperature. Above the Curie temperature only the ferromagnetic material will become a paramagnetic material. So above the Curie temperature the susceptibility will be inversely proportional to T minus Tc. So what do you mean by T here? T means the absolute temperature. Tc means the critical temperature or the Curie temperature. Right? As critical temperature increases above the absolute temperature, right? What happens? The susceptibility starts decreasing. Is it clear? As this increases, this decreases. So T means the absolute temperature, Tc means the critical temperature. Again, in order to eliminate this proportionality sign, we'll take a constant C, which is called as Curie constant. Right? So this is about the Curie-Weiss law. Next we'll study regarding the properties of ferromagnetic material, paramagnetic material and diamagnetic material.